Good morning, students. Welcome back to discrete mathematical structure classes. So previously we seen logical implication, rules of inference. Okay, and we had seen an example and proving that one into using a truth table. And this is one more example we have seen. This is using truth table we proved and we found it is going to be a tautology. Okay, now we'll go with the definition. Definition of logically implies. Okay, so if P and Q are arbitrary statements such that P implies Q is a tautology, then we say that P logically implies Q. Okay, so how we are going to represent it? P logically implies Q. Okay, so what has been given? P and Q are two arbitrary statements. Arbitrary statements here means it can be a primitive statements or it can be a arguments also. Okay, such that P implies Q is a tautology. Okay, so whatever the value I'm having here, this one and this one, they are logic. P implies Q. This if we find implication of this one and it is must and should be resulting into tautology, then we say that P is logically implies Q. This P logically implies Q. Symbol for this one you can see. We are going to use this one only. Okay. Then when PQ are statements and P logically implies Q, the implication P implies Q is must and should be tautology. Vice versa. If P implies Q is tautology, then it is called as a logically implies. Now, if any statement is logically implication, then there P implies Q must and should be tautology. Okay. In the previous example, we found that for primitive statements, PQ implication, P implies P or Q is a tautology. So, we say that P logically implies P or Q. That is nothing but in a representation we will be having like this. P logically implies P or Q. Okay, from the first substitution rule, we also find that P logically implies P or Q for any statements P and Q, that is P implies P or Q, is a tautology for any statements P implies Q whether or not they are primitive statements. So here we can have either P or Q and they can be any other primitive statements also. Okay, next let us take one more example. So it is let P and Q be arbitrary statements if P logically implies Q, means it is also going to have a same value and it is also going to have same value, or it must be having 0 and this must also be having 0. Then what we can say is P logic biconditional Q is tautology. Of course, when it is 0 0, biconditional value will be 1. If it is 1 1, here also it is going to be 1. Okay, so in that condition what I can say is both the value I'll be getting as 1, so we can say it is tautology. So the statements P Q have the same truth values. So what we can say is P implies Q and Q implies P are tautologies. Hence we can say is P logically implies Q or Q logically implies Q. So both are going to be valid one. Fine. Next, let us take one more. Suppose that P logically implies Q and Q logically implies P. Means this is also having same value, this is also having same value. This is also having same value, or this is also having the same value, or it can even have a 0 0 also. Both anything having, but they are going to have a same value. This is also 0, this is also 0, this is also 0. Any combination it can have. This combination or this combination. The logical implication P implies Q tells us that we never have a statement P with the statement truth value 1 and statement Q with a 0. Means they are not going to be different. They must and should be either 1 1 or 0 0. Here also it can be 1 1 or 0 0, but never 1 and 0 or never 1 and 0 or 0 or 1. If this occurred, we could not have the logical implication Q implies P. Okay, that's not going to be satisfied. Therefore, when P logically implies Q and Q logically implies P, the statements P comma Q have the same P by logically equivalent to Q. Finally, the notation P logical implication, not a logical implication Q, indicates that P implies Q is not a tautology. So given implication P implies Q is not a tautology. Okay, understood? So they must and should be having both the values same, either 1 1 or 0 0. Then only I can write they are biconditional, also they are logically equivalent. Otherwise I cannot tell if it is going to have a 1 0 or 0 1 combination. I cannot tell anything like that. They are not going to be that time even tautology also. Fine. Next, finally, the notation P logically implies. Okay, ಇದನ್ನ ಹೇಳಿದ್ದೀನಿ. Next, we'll come to here. Next example, by De Morgan's law and the first substitution rule, we know that for P comma Q, we have negation of P or Q logically equivalent to negation of P and negation of Q. This we already learnt. I think you all of you have written a truth table. Okay, we know they are logically equivalent. Now consequently, here we have taken disjunction, we'll take here for conjunction. P negation of P and Q logically implies negation of P or negation of Q. Why we are taking? Because we know they are logically equivalent. This is first De Morgan's law and this is going to be second De Morgan's law. Okay, so both I am written since they are logically equivalent. I can in between I can put here in between logically implies. Here also I have put a logically implies. If they are logically equivalent, of course this complete value is going to be 1. This complete value is going to be 1. So both value are going to be same. So in between I can say is they are logically implies, or I can say it is logically equivalent. So or else one more thing I can say is this particular part and this particular part, if in between if I put a biconditional, it is going to lead to tautology. Following? See what the work I have done this with yellow color pen is, you are going to see, not the black, and don't mix up here. Okay, I'm just extending here. Following? Okay. P and Q are alternatively because each of the implication. Hope all of you understood. Okay, next we are going to have a rules of inference. So first rule of detachment. It is also called as a modus ponens. Why it is called so? Because consider the rule of inference called modus ponens, the rule of detachment also it is called as. It is being derived from Latin, may be translated as the method of affirming. Okay, so that's why the name is modus ponens. So what we are going to do? So one thing you observe here, we are going to represent all conjunctions. Okay, your next slide or next examples you are going to see it. We are going to represent this one in a tabular form. Okay, so we are going to have, this is first P and this is P implies Q. This is one part. In between I'm having conjunction and then we are going to have a implication. Okay, so we'll check its value. So PQ only two primitive statements, so 4 rows. P implies Q, then P or this complete statement, for that one I am going to write here. then final. So look at here, all the value are, all the value are 1, means it is going to be a tautology. When it is tautology, we can say it is as, I'll write here, it is first P I'll take here, then I'll write here P, then I'll write P implies Q, then divide, it is going to be after implication whatever is there, that is conclusion. So I'll write here using these symbols, then I'll be writing that one as Q. Okay, so this particular part is going to be called as a tabular form of a rules. See, here it has been given. Here the fourth row is the only one where both of the premises P and P implies Q and conclusion are true. The actual rule written in a tabular form. How? P or P implies Q, therefore it is Q. Where therefore stands for the therefore, indicating a Q is the conclusion for the premises P and P implies Q, which appear above horizontal line. This rule arises when we argue that if P is true and P implies Q is also true, or P logically equivalent to Q, or P logically implies Q, then the conclusion Q must also be true. And one more thing here is P and P implies Q implies whole implies Q is tautology for the primitive statements. That is the statements present over here. From the first substitution rule, replace P and Q with the help of R or S and negation of T and U. Okay, so what I'll be getting? P with the R and S, and here also P that has been replaced. Then Q places negation of T and U. So therefore I'll be getting here is conclusion Q. So this is also conclusion. E is also a valid argument. By which law? By rule of detachment. Okay, and if you check, this one is also going to be a tautology. You can just verify. That is going to be your homework. Okay, so this next law we are going to have is law of syllogism. So when law of syllogism, what we are going to have is, here is a P implies Q, another Q implies R, then whole implies, you can see here, whole implies P implies R. So this is P implies Q, Q implies R, therefore P implies R. Okay, how we are going to write? Let's take an example. If the integer 35,244 is divisible by 396, then the integer 35,244 is divisible by 66. So there is a this is if I call this one as a P, and if I call this one as a Q, so I'll be having P implies Q. Similarly, next line, if the integer 35,244 is divisible by 66, that is Q, and then the integer 35,244 is divisible by 3. So this is different, so I'll represent this one as R. Okay, therefore if the integer 35,244 is divisible by 396, then the integer is divisible by 3. So therefore we are going to have P implies R. See, looking at here, what I can say here is, I'll just change the color of this one. Okay, so P is here, Q is here, and Q is here, R is there, P implies R. So when we are going to have the law of syllogism, this part is going to be removed and retained this part, and they are here. P implies R. Following example, Rita is baking a cake. I'll consider this one as P. if Rita is baking a cake, then she is not practicing her flute. So this remains P only. Okay, and she is not practicing her flute. I can take this one as Q. Since there is a not, I'll make that one as a negation. So it is going to represent negation of Q. Then if Rita is not practicing her flute, means this is part. So this is going to be again negation of Q. Okay, then her father will not buy her a car. Okay, so this is a new word. So P got over, Q got over, I'll take a R. Okay, so again there is a no is there, so I'll take that one as negation of R. Then therefore Rita father will not buy her a car. So this is going to be same thing, so it is going to be negation of R. What we have done, I have taken here directly, but if you do like this, you are not going to get a full mark. So what we have to do? So we have to write, I'll show you. Um, so first you have to write from the given solution, you are going to write before this particular statements you can write here. We assume that P is Rita is baking a cake. Q is she is not practicing, she is practicing her flute, and negation of Q is she is not practicing her flute. Okay, then next one R is her father will buy her a car. R is the negation of R is her father will not buy her a car. Okay, if we write all of these things, then let us represent that one in terms of this symbolic form. Okay, then once it is done, since it is in a tabular form, each row whatever we are going to have is going to be represented separated by the conjunctions here. I'll here P, and P implies Q conjunction, negation of Q implies negation of R conjunction implies negation of R. Okay, then we have to simplify this one because we can apply any law, we should get a conclusion. Okay, so first we'll take here. So always while simplifying such kind of a using rules of inference, what we have to do is make a two columns. There is no mandatory, but you can make a two separate. So first one you can write steps, another we can write reasons. So first step, first whatever is there, I'll take that. It's not mandatory all the time you have to take the first one, but whatever first you are taking, you are going to write that one as a premises, and all the premises must and should be used. Premises are which all are, this is, I'll just rub it. Okay, so first this is one premise, this is another premise, this is one more premises. Okay, so I can use any of them. So first I'll take a this one, P implies logical negation of Q, the second one. Okay, then negation of Q implies negation of R, that one also I'll take. Now compare this one, can I apply, we have learned two laws, one is law of syllogism and law of detachment. So this is common, this is common, so I can take these two using a which law, law of syllogism. So from which all steps, this is first premise, this is second step. So step 1 and step 2 and apply law of syllogism, I'll be getting P implies negation of R. Okay, once it is done, next left out is which one? Next left out is this premises. So I'll take that one, I'll write here. Then I'll say I know rule of detachment. What is it? P implies negation of R followed by P. Conclusion I'll be getting as negation of R because P is going to be detached. So I'll be writing step, this one whatever I got is step 3 and 4, and rule of detachment I got is this one. Understood? Okay.